In our last video, we went through the process of iterated integration, where we integrated the inside function first and then took the integral of what we were left with. In this video, I want to talk about what this calculation actually did. And so let's think about the integrand, the function on two variables, that is f of x comma y equals x squared plus y squared plus 3. Well, if I think about that function in space as a graph, that's a paraboloid. That's a circular paraboloid shifted up 3 units. And I happen to have crudely sketched this paraboloid, and when I did it, it was kind of tilted, so please forgive that, but there's my elliptical or circular paraboloid in this case. And I've also kind of written down highlights from that previous calculation. This was the original iterated integral. And now what I have is, skipping all the work, what that inside integral resulted in, and then the final answer. So let's talk about what this does. So if I just think about the inside integral for a moment, the integral from 2 to 3 of x squared plus y squared plus 3 dy. The only variable, as far as this integral is concerned, is y. X is going to be treated like a constant. And if I cheat just a little bit, and I look at the outside integral, I can actually tell you for sure that x needs to be between 1 and 4. That on the x-axis, I'll be considering things between 1 and 4. So x is just some value between 1 and 4. This should really be parallel to the y-axis, but we'll just pretend. All right. So that's what I know about x. Well, if I plug in a value for x, then I will get a value of this definite integral, right? Like right now, I just evaluate this and I get x squared plus 28 over 3. If you give me a value of x, I will actually get an answer, a value for that, which tells me this is really a function on x, right? I do all this, I get x squared plus 28 thirds. If you give me an x, I'll actually get a value. All right, well, x has to be a number between 1 and 4, and so that's the domain of this a of x. Let's imagine we actually fixed a value of x. Let's just say x naught between 1 and 4. And think about what a of x naught would represent. Now, I'm being very leading with calling this a. It's a function. But if I imagine x naught, well, x equals x naught defines a plane, and I could actually think about where that plane intersects my paraboloid. And as it goes out, it would trace out a parabola on my paraboloid. In particular, it would trace out x naught squared plus 3 plus y squared, right? I would get that parabola. All right, well, what's this doing? Well, I'm in the plane x equals x naught. This is a definite integral of a function that's positive and is something that looks like a yz plane. It's telling me the area over the line x equals x naught under that parabola. All right, but not all the stuff I just shaded. That's fixing here, right? That goes on forever for that x naught. I know y is supposed to be between 2 and 3. And so my y values between 2 and 3 just narrow us down to this little rectangular region in the xy plane. And so for that particular x naught, I would get this area, the area of this strip. All right, so all of that to say, if I fix x equals x naught, my graph of z equals x squared plus y squared plus 3 would become a parabola in a plane that's parallel to the y-axis, something that looks like a yz plane. And this definite integral is telling me an area in that plane beneath the curve, just like it did in Calc 1. So now I can think of this definite integral, or this one, as being a definite integral in the form of the integral from 1 to 4 of a of x dx. Well, that's taking a bunch of areas and adding them together. The definite integral of an area function is a volume. And so this iterated integral is actually telling me the volume of the region under the paraboloid but over this rectangle. So you could imagine all of the little regions that go up and hit a parabolic region under that surface. So you can imagine a rectangular prism coming out of the board and taking a parabolic scoop out of it that just forms the same shape as the side of this paraboloid. So an iterated integral is actually giving me a volume. One cool thing to consider, the argument I've used here was to integrate with respect to y first and then x. The same argument would hold if I swapped the order of integration. So this is the same problem I had before, but I've changed the order of integration. Now, I'm integrating with respect to x first, and the x bounds go with the dx, and the y bounds go with the dy. I claim if you do this process again, you should still get 49. And I'm going to leave that as something for you to try. Do the integration again, but with the order of integration reversed, and you're going to get the same volume. In our next video, we're going to connect iterated integration with something called double integration.